hopefully you all were able to write this hello world program, to type in those constructs, and to run it. And so you now have a multi-threaded program, and that top thing is the include file, OMP.h. That has the function prototypes for any runtime library routines, links and special types it needs. That directive, pragma OMP parallel, that's how we're going to create threads. And oh my God, I will go through that in a lot more detail later, don't worry. And then we have that block to close it. And when I ran it, I got something like this. Hello, hello, world, world, hello, hello, world, world. And each time I run it, I get something slightly different. All right? That's what I got. Now, is that similar to what some of you got? Yes?
So even if I don't include OMP.h, I can still compile it and run it.
I'm sorry, what was that?
Even if I didn't have include OMP.h statement?
If you didn't include the OMP.h, it still might have worked, because in this particular program, so the question was, what if I forgot that OMP.h? Would it still have run? And in this particular program, it would have. Remember, that include file in the C programming language, its major purpose is you have runtime libraries, things you need to tap into in the API you need to tap into in your code at runtime. And the function prototypes for those are in that .h file. Notice here, we just put one directive in, no library routines. So this may not have needed it. So it probably would have worked without it. OK, so I want to say a little bit, because I'm embarrassed that my chosen vocation, my calling in life, parallel programming, our relationship to jargon is so screwed up, it pisses me off. So I'm going to try and set the record straight right now. So let's talk about some jargon. A computer, OK? Look, a computer is a machine. It takes input, and it generates output. And we can get really, really fancy, but you got a control unit, arithmetic logic unit, memory, and it just converts input into output. I'm going to use the word task to refer to a logically related set of instructions that that machine processes and its data environment. That's the word task. The word active task is a task that is available to the machine to schedule for execution. Now, this last word is really, really important. If the set of tasks that are available for execution are given equal access to an execution slot, we say that they are fairly scheduled. This is a very important concept. I have, 150 different tasks that my operating system knows about. And what it does is it bounces. I'll do this one, I'll do this one, I'll do this one, I'll do this one. So they're bouncing along, and they're giving a roughly equal quantum of time for them to execute. If the machine does that, we say that you have fair scheduling. And you're going to see in a moment why I make a big deal of this. All right, so let's talk about the words concurrency and parallelism. By the way, my #1 favorite job interview question, because I am hiring, my #1 job interview question is define concurrency. And no one's gotten it right yet. So that's why I'm trying to set you all straight. All concurrency means, literally all concurrency means, is it is a condition of a system where multiple tasks are active and unordered. Okay? You do not know what ordering is occurring between instructions in those multiple tasks. That's all it means, period. And this is the definition going back to the 1970s. Don't go around changing it. Okay? Now, if they're scheduled fairly, then they're making, logically, they're making forward progress. Now, the problem is that lots of people, they define concurrency as unordered, fair scheduled forward progress. And it's important that those are different concepts, and you will see why in a moment. All right? So concurrency just means a collection of tasks, they're active and unordered, period. Stop. Okay? Parallel means a collection of tasks that are actually making forward progress at the same time. That's the difference between parallelism and concurrency. All right? And here's why this is important. If I look at the universe of programs, I have programs that are just any program you could write. A subset of those are programs that can contain concurrent tasks. A subset of those are programs that contain concurrent tasks that execute in parallel. But now look at that little bitty bit of the Venn diagram that sticks outside. I can have programs that are parallel but not concurrent. So if I'm going to really talk about the universe of parallel programming, I have to be able to talk about concurrent programs that are running in parallel programs that aren't concurrent. Now think about the SIMD unit in your CPU, for example. All right, you have the lanes of that SIMD unit, and they're strongly ordered. There's no unordered there. You know, everyone in a lane does this op, then everyone in a lane does this op. Lockstep execution. Okay, so I can have parallelism that's not concurrent. Okay, when we talk about GPUs late this afternoon, we can have concurrency without fair scheduling. Because if I look at if I use CUDA jargon thread blocks, if I use rational jargon work groups, we'll get to that later. I picked on Apple in the morning, I'll pick on NVIDIA in the afternoon. Okay, seems fair. So at any rate, I can have concurrency, and this is like in the systems you will touch, you can have cases where you have concurrency without fair scheduling. So you have to be able to hold in your head these concepts as separate, because it can be very important in understanding what a system's doing. Are they concurrent? Yes, no, okay. Is there fair scheduling? Well, that means I can do this. There isn't fair scheduling? Whew, I can't have a spin lock then. So there's very practical implications to keeping these terms straight. All right, so now, when we think back to that example, and it's too hard to go back and forth, but when we think back to that example, there we go, with the hello, hello, world, world, okay? I had those as different print statements. Threads are concurrent, and they are fairly scheduled. So they are unordered, but because they're fairly scheduled, I know they would each get through their full execution. And that's why I get that order. That's why each time I run it, I can get a slightly different order. So remember, threads execute concurrently with fair scheduling, and you will understand threading. Now, the challenge this is to you as a programmer is you have to make sure, and this is really, you know, I can leave you today with the impression that OpenMP is the easiest thing in the world. Oh, God, this is easy. No, it's not. It's not easy because when you start getting to complex programs, you have to look at the code and analyze it and know that every single way that those statements could be ordered would still be a correct program. This is the hard part of multi-threaded programming. And we will have lots and lots of times today where you will learn about that. All right? So your job as a programmer is to write code where every single way the statements are ordered is still a correct execution. And that can be challenging. Okay, questions at this point? Yes, oh, a question. Yeah. Can I repeat about what I said about what? I'll repeat what I said about threads and concurrency because this is a vitally important concept for you to have completely nailed in your head. Okay? Anytime someone is talking to you about multi-threaded execution, and this is why I'm pissed at NVIDIA for their use of the word thread. I had a long fight with them about that. I lost. Okay? They're very smart people. CUDA is gloriously wonderful, but to call what they have threads causes a huge amount of confusion. Okay, so when I'm talking about running on any CPU with a shared address space multi-threading programming model, the threads are concurrent, which means there's a collection of threads that are available to execute, and they're unordered with respect to each other, so they're concurrent. But because the operating system schedules them fairly, you know each one of them will get an equal shot at running. So they're fairly scheduled concurrent. Okay? So so any multi-threaded programming model, you know, you get in your head, okay, the execution is multi-threaded, is multiple tasks that are concurrent. All right, let's talk about creating threads. So one thing I'm really big on is the way you achieve mastery in any subject is to understand the foundations and the fundamental patterns that you can pick up with you and carry to other contexts. So anytime I'm talking about a multi-threaded environment, so multiple tasks fairly scheduled that are concurrent, the classic execution model is fork-join parallelism. Okay, people, this is the way people thought about multi-threading for years, long time. So the idea is you start with an initial thread. It's cruising along, it's doing its thing, and then it comes to a point in the program where it could benefit from having additional threads. So then it forks off those threads, and that's the term we call they fork those threads. So now I have a parallel region. So that's those threads working together. We call them a team of threads. So I create a team of threads, and now they execute concurrently. And if I have multiple cores in parallel, and then when they're done, it's like, OK, we finished that work. They then join back together again. So it's a fork to create the threads, a join at the end. And then that initial thread continues. And it may hit another piece of the code where it would benefit from having additional threads. It forks the threads, creates a new team. Notice the teams do not have to be the same size. You can have different sized teams based on the work, based on the needs. And so your program becomes this sequence of parallel regions separated by sequential parts. So that's what you get. We talk about the sequential part is in between those teams of threads. A parallel region is when the team of thread is executing. Now, parallel region, the term region, we're talking about all of the code, even inside functions that are called. We'll come to that in a second. Okay? And yes, they can be nested. So a thread in a parallel region could cruise along and go, you know what I really need is a couple more threads. I can fork threads in the middle of a parallel region. So we can have nested parallelism if you want it. So the construct to do this is the parallel construct. So I have your code. Imagine I create an array. I have a library function called OMP set num threads. OMP set num threads is a runtime function call that says, please give me 4 threads. So OMP set num threads, it changes the default number of threads. And it tells the system, unless you hear otherwise from me, when I say create threads, I want 4 of them. So that's what OMP set num threads does. So then I have pragma OMP parallel. And in between those brackets is the code. And every thread will redundantly run the code in those brackets. It's very simple. And inside, you see I have another runtime library function. So this is where we need the OMP.h at the top so that it knows to access those runtime library functions. OMP get thread num. OK, so that's going to return an integer that ranges from 0 to the number of threads minus 1. In MPI speak, it's the rank of each thread. And you'll do MPI tomorrow. MPI is awesome. Okay? I like it almost as much as OpenMP. Sometimes I like it more than OpenMP. But don't, oops, we have a video on that. I didn't really say that. Okay? OpenMP is the best. Okay. Phew. So every thread in this code is going to get its ID, and then it's going to call that function poo. Now notice, well, let's walk this through. Rather than me talk it through, let's walk it through looking at code. So in the yellow box, I reproduced the code from the previous slide. And let's talk about exactly what happens. OK, so each thread's going to execute the same code. So the compiler will look at the code between those brackets. It'll outline it. It will pull it into a function. It'll have a team of threads. It's going to use the pthreads fork. It'll hand the function pointer to each thread, so they're all going to run that code in that block. Now, if I declare a variable outside the team of threads, so see that int a double, okay, an array of size 1,000, that's in the shared memory. All threads see it. All right, so if I declare a variable, and there's tons of exceptions, we will laboriously go through it in detail later on. But to first order approximation, if I declare the variable before the parallel region, it's shared. If I declare the variable inside the parallel region, it's private. It's local to the thread. So in the execution of this code, I'm going to create, let's say I get the number of threads I asked for. So I got 4 threads. And they have an int ID. Remember, there's the int ID equals OMP get thread num. So the thread with rank 0 gets ID 0. The thread with rank 1 gets ID 1. You get the idea. So now when they call that function poo, when they call that function poo, it's going to be 0A, 1A, 2A, 3A. Now when you get to the end of it, so all the threads have finished running the code, we have a barrier there, so they all wait, and once they're all done, the initial thread continues. Now, does this make sense? Now, at a few points today, I'm going to have what I call a head nod moment, because it defines a point in the tutorial where I have to know absolutely that you're with me. So this is our first head nod moment. Is this okay? Do you all get it? What didn't you get? What? Oh, you didn't nod your head. When I say head nod moment, I need to see, yeah, okay. All right? Remember that. Okay? Okay, so you all know OpenMP. That's it. All right? No, there's going to be a little bit more. A lot of subtle details. So let's be clear, and I was careful in my language, but let's be absolutely clear. When I do that OMP set num threads, you are requesting a number of threads. In OpenMP, it's built in the concept that if you're running on a large shared system, you know, because some people don't know how to keep their air condition running and we lose our machines, so now you have to go off to some who knows where server, and there may be 20 of you on single node, which has 16 cores, but there's 20 of you using it. The operating system can go back and say, I know you asked for 100 threads, but I have to be share. You have to learn how to share. You obviously didn't learn that in kindergarten. Sharing's good. So I'm only going to give you 2 threads. Right? So we built into OpenMP that the operating system can choose to give you fewer threads than you asked for. It will never give you more, but it can give you fewer. So what I have to do, if I'm writing code that needs to know the number of threads, I have to have a way of asking, in this parallel region, how many threads did you actually give me? So you can see, and I think the next slide builds that out. Yes. I have a runtime function, OMP get num threads, and that runtime function returns the actual number of threads in the team. Okay? So if I'm writing code where I need to know the number of threads, that's the function I call. All right? Pretty straightforward. See, isn't this all really easy? Okay, well, let's go on to our first example. This is the Hello World program of parallel computing. If you've done any parallel programming, you've probably seen this code. We love it. We love it because it lets us draw pretty pictures. It lets us put integrals on a slide. And I can tell when I have the computer scientists in the audience because they see an integral and they go, oh. No, I'm sorry. I have to be careful. I have been criticized for picking on computer scientists before. Okay? If you're a computer scientist, I'm really picking on myself. Okay? Deep down inside, I think of myself as a physicist, a physical chemist. I support myself as a computer scientist, and that's a personal failing. And I take it out on computer scientists. That's not fair. So, okay, really, I have nothing against computer scientists. Some of my best friends are computer scientists. So, at any rate, we're going to sum up the area under that curve. And the beauty of this is that if you do everything right, it actually goes faster as you add threads. So that's cool. And you have a way of quickly testing the answer. The answer better looks something like pi. So it kind of has everything you're looking for. You know, it can go faster with parallelism. You can know if you get the right answer. But equally important, the code fits on one PowerPoint slide. Okay? Never discount the value of code fitting on one PowerPoint slide. So that's the code. And in the repository, I have that code for you. So those of you who are not fluent in C programming, that's okay, because I give you the C code to start with. So here is your assignment. Oh, one more concept. Yep, one more concept, then comes the assignment. I want you to be able to time code. Okay? So we added a timer in OpenMP. And we based it on the MPI timer. So there's a reason. MPI came right before OpenMP. So when we were creating OpenMP, people like me did both. You know, I was part of the group that made MPI, and you know, I'm part of the group that made OpenMP. So we made it so it looks just like the MPI timer, and you use it the same way. So OMP get W time. I think of the W time as meaning wall clock time. Just to make clear, it's not the number of cycles the CPU spun for you. It's like, no, if I looked at the clock and I took a snapshot, then I do something, then I look at the clock and do another snapshot, their difference tells me how much time it took. So that's the OpenMP W time. Now we get to the assignment, okay? What I would like you to do is just using those 4 runtime functions and the Pragma OMP parallel. Nothing else, those of you who know OpenMP, just use those. Create a parallel version of that Pi program. Now, this can take a while. For those of you who are experienced parallel programmers, you'll be done in 10 minutes, maybe 5. For those of you who have never done parallel computing before, don't feel bad. This can take you 20, 30 minutes. All right? There are some big conceptual hurdles in this exercise by design. So go for it. I will come back to you in 10 minutes or so with hints if you're stuck. If you're blasting through this really quickly, don't be shy about going around the room and helping. I like a room to get noisy at this point. All right? And this is the block of time for those of you who still don't have an OpenMP compiler you can use. This gives us a block of time to take care of that. So let me know if you're one of those people, and we'll figure out what we're going to do. All right? Good. Go for it. The Pi program. Here is my solution. So 2 issues you have to solve. How are you going to break up the loop? How are you going to handle the accumulation into that shared variable? I described it to someone else who had a question, but let me explain something. It's a term you need to know in multi-threaded programming. And that is, if I have multiple threads mixing reads and writes to the same location in memory, remember, variable is just a name for a location in memory. So if I have a mixture of reads and writes to a same location in memory, and they are not ordered, I have not gone through and said, nope, this guy can do it. You wait, man. Wait until he's done. OK, now you can do it. So if I don't put in those order constraints, it is undefined, the behavior of the program. And it is an illegitimate program. That's true in C, C++, Fortran, OpenMP, OpenCL, SYCL. It's now the standard get-out-of-jail-free card that compiler writers use. Pisses me off, actually, and we can talk about that later. Because they literally say, we don't have to do anything. And they just ignore the fact that it's really hard to write a program that doesn't have race conditions. So you really have to take that into account. So watch what I did here. So I set the number of threads. I did a pound define num threads 2. And then what I did is on that variable sum, I made it an array indexed by the number of threads, the maximum number of threads I'll ask for. So we call this promoting a scalar to an array. It's the oldest trick in the book for this sort of thing. Because now what I've done is it's still a shared variable. It's still visible to every thread, but I've created a separate piece of it for each thread. So now in the body of my loop, if we jump down near the bottom of the page, you can see that instead of just sum, accumulating, sum plus equals, I have sum of ID plus equals. So now I've created a safe spot, no data races. Each thread has its own little location in shared memory that it is accessing and no one else. So that's how I solve that problem. And so then when I'm done with the parallel region, I combine all those values to get the final value of pi. So that's how I solved problem 1. Okay? Problem 2, you have to split up the loop. Because if you have each and every thread going through and doing all the iterations, you'll get the right answer, but you're not doing anything in parallel. Or you are doing things in parallel, right? You're doing lots of redundant work in parallel. Okay? But your program will not run faster. It'll run slower as you add more and more threads, probably. OK, so you have to split up the loop. Because I come from an MPI background, I used the oldest trick in the book that we knew from message passing back in the 1980s. Yes, I really am that old, 1980s. Okay. So, and that is called the cyclic distribution of the loop iterations. Look at the trick I did. So for my loop control index I set I equal to the thread ID. Okay, I left, going to continue until as long as I is less than the number of steps. But then look what I do is I increment by the number of threads. Okay, so if I had 4 threads, one's going to do thread 0, thread 4, thread 8, thread 12. Another one's going to do, iteration 1, iteration 5. Okay, easiest way to split up loop iterations. Now, what I bet most of you did, and it's equally correct, in fact, in some ways better, okay? You can also compute, okay? I've got this many steps, that many loop iterations divided by the number of threads. Now I can set begin here, end here, perfectly fine, all right? That's perfectly correct, and I'll have that solution later, actually, all right? But somehow you have to split up the loop iterations. So now another thing you have to think about is where else could I get a data race? And one of them is with x. Notice that I have x equals, I minus 0.5 times step. I have to make sure each and every thread has its own copy of x. Each and every thread has its own copy of I. Okay? You have to think about those things. So that's why I declare them. I have int I have the double x. So this version of the program runs. And I get, running on my laptop long, long ago. It's an old laptop. I get 1.83 seconds when I run this without OpenMP. It's always good to check that. What do I get if I don't use OpenMP? Where's my starting point? Because when you introduce OpenMP, you're linking in the OpenMP runtime library. You're linking in other stuff set up so it's ready to take threads. So there's always some overhead that the parallel programming model adds. It's a little tax you pay. So notice it was 1.83 seconds without OpenMP. It was 1.86 seconds with OpenMP in one thread. Well, that's not very much. It's not very much at all. It's very tiny. And then I go to 2 threads. It's 1.03. 3 threads, it's a little slower. 4 threads, not great speed up. Not great speed up. We'll talk about that, believe me. But at least it sped up, and it gave me the right answer. And it's a beautiful little program, isn't it? Isn't it beautiful, right? Okay. Now, I'm really big, though, on what are the fundamental design patterns. What's the nugget of designing this algorithm that I can carry with me to every programming model I move to in the future? This pattern is called the single program multiple data pattern. What I basically did is I replicated the code, so instead of one instance of that block of code, I had, in this picture, 3. And then I thought about the problem domain. In this case, there's no data, but there's loop iterations. And so I'm running the same code, but I make sure that each thread is seeing a different block of those. All right? And all I'm using to do this is replicate the code, figure out how many threads or how many tasks are running, and then using the ID and that number of threads, I split up the WRP. And it's very simple. And by the way, this is how you write MPI code. All right? Now an MPI purist would go, well, but what about the new wanked, far out, weird new construct we added, and this bizarre through the butt kind of backwards reverse transcriptase, Yes, they have all this new stuff, but the overwhelming majority of MPI codes that are out there, and the overwhelming majority, almost 100% of the ones you write, will use exactly this pattern. So do you see how awesome this material is I'm presenting to you? Because not only do you know OpenMP now, you now know MPI. All right? Okay, there's the spelling of the constructs, but this is how you do MPI. I think that's cool. All right, we're going to take a break, and when we come back from the break, we'll start here. But we need to take a break. We will start again at 10:30, so it's a 26-minute break. Is that okay that it's not 30? Well, it doesn't matter. That's what we're going to do. I just hope you don't get angry with me. And those of you who didn't get all the way to pi, now that you saw my solution, think about your own solution and finish it your way.